All right, we left off with the diprotic acid. Where your concentration of your A minus 2, a very important thing to know, is always equal to your Ka2. All right, so we went through this last time. So this was our diprotic acid, and I always call a diprotic acid H2A. Here they call it H2ASC, or just abbreviating the name of the compound. But I always use H2A. And then we got our value for Ka1. You always do Ka1 first, get your numbers from Ka1. And what you're going to find is that is your final answer for your H3O plus and your HA. I call this HA minus. So when I'm doing my equilibrium, I have H2A, where the first one goes to H plus and HA minus. All right. And to confirm that we can use successive approximations without checking, we're going to do the concentration initial of your acid divided by the Ka of the acid. In this case, it's Ka1. So my initial concentration, and that has to be greater than 100 was wrong. It has to be greater than 1,000. All right, and so the concentration of your acid that you started with, initial concentration, 0.1. The Ka is 7.9 times 10 to the minus 5. All right, and so that's going to be in the thousands. This one is going to be good. 0.1 divided by 7.9 times 10 to the minus 5. That's going to be at barely good. You get about 1,300. So when you divide that, you get the 2 sig figs, 1,300. All right, so basically if it's over 1,000, not 100, over 1,000, then you do not have to check your X value. And in this case, it might change, but again, if your value is greater than 1,000, you do not have to check your X. If it is less than 1,000, you either do successive approximations and check them, or you do the quadratic equation. All right, and so now we multiply both sides by 0.1, take the square root, and that gives us our X value. All right, and that is 0.0028. All right, and so you can then also check that and say, well, I said that my 0.1 minus X is not going to have any effect. And if you use the sig fig rules and you take your 2 decimals and subtract your 4 decimals and you give your answer to 2 decimals to the correct number of sig figs, it does not change. Your 0.10 remains as 0.10. All right. Now, they immediately go to pH here, which is a little bit of a jump because you still have Ka2. Well, you find out that the Ka2, the amount of H plus that you get is insignificant. It will not change. So your pH always comes from the concentration of H plus from Ka1. And so when you take the negative log of your 0.0028, your pH is 2.55. All right, now to confirm that is the case, we do our Ka2. So in Ka2, you have your HA minus in equilibrium with your H plus and your A minus 2. All right, so now your initial is from Ka1. We had HA minus was 0.0028, H plus also 0.0028. The A minus 2 was not part of the Ka1, it is 0. And so now instead of calling them both x values, we're going to call this one a y, which is fine. It's just another variable, but you don't get confused with that was x and so was that. All right, so we're going to say it has to go to the right because you cannot have 0. All right, so minus y plus y plus y. And at equilibrium, you have your 0.0028 minus y, 0.0028 plus y, and y. You stick that into the Ka2 expression. All right, the Ka2 expression. And if you want to check to see if we can omit the plus y and the minus y without checking, again, here you're going to take your concentration of A over the Ka2. All right, so you're starting with 0.0028, and the Ka2 is 1.6 times 10 to the minus 12. I don't have to push the buttons to know that that is way more than 1,000. So you got minus, that's something times 10 to the 9th. So it doesn't matter what the number is. It has to be over 1,000. And when you're times 10 to the 9th, you are way more than 1,000, which means you can eliminate your plus y and your minus y because that is not going to change the number at all. And then you see you got 0.0028 in the numerator. You have 0.0028 in the denominator, and they cancel. And so you have your answer for y. It is simply the 1.6 times 10 to the minus 12, which is your Ka2, which is equal to your concentration of your A minus 2. So again, anytime you have a diprotic acid, if you want the concentration of your A minus 2, it is always equal to Ka2. You can go through all these steps and calculate it. Or if it's a multiple choice and it says, what is the concentration of the A minus 2? You just look at the Ka2 they give you, and that is your answer every time. All right, but once you put that as your answer, concentration has the units molarity. Kas do not require units, but your concentrations will, and that is always molarity. All right, now again, so we had our concentration of H3O plus, which now we know is 0.0028 plus the y value, 1.6 times 10 to the minus 12. That doesn't change that number at all. All right, so you've got your 4 decimals and you've got your 13 decimals, and so you give your answer to 4 decimals. It doesn't change. And so, yes, your answer for H plus, all of that comes from the Ka1. So that's 0.0028 molar for H plus. All right, so that confirms that you do not need Ka2. So if you have a diprotic acid and ask for the pH, you just have to do Ka1. Ka2 will never change the concentration of H plus enough. It increased it by such a small amount. If you use your sig figs, it doesn't make any change at all in your concentration of H plus. So if you just want the pH, you just have to do Ka1. If you want the A minus 2, you don't have to do anything. You just find Ka2, and that's your answer. So your A minus 2 concentration is always equal to Ka2. All right. So now we're going to do some base ionizations. All right, and so here we're going to have a weak base. All right, so we're going to have a weak base. And you need to know that ammonia is a base. All right, so if you don't know ammonia is a base, you need to know that ammonia is a base. It is a very, very common weak base. So if we stick ammonia in water, what we can say is, well, we know the pH is going to be greater than 7. You stick a base in water, pH has to be above 7. All right, it is basic. All right, generic, all right, they're going to use a different generic code than I do. And so I'll go to the next slide. I'll show you the generic. All right, so the generic that they use that I will not use, you can use it if you want. I don't care. I like to have, okay, for my acid, I use HA and I use A minus. And so for my base, so HA is my weak acid, my A minus is my weak base. So I want to use that terminology for my weak base. So instead of using B, I always use A minus. All right, the plus H2O is the same. All right, and so instead of HB plus, I use HA. All right, so I use the same conjugate acid system in both my Ka and my Kb. All right, and so plus the OH minus. Again, it's generic. If you want to use B and HB plus, fine. I will not be using that. I'm going to use A minus, and plus H2O goes to HA and OH minus. Those are the ones that I always use. I think it's the best. You can use the other one. There's nothing wrong with it. That is not the one I will use, though. All right, so my Kb, all right, so they have their Kb. And remember, water is a pure liquid. You are not going to put that into your setup. So my Kb is going to be my HA concentration, which is exactly the same as their HB plus, OH minus concentration, all over my HA. No, sorry, A minus. All over my A minus. All right, so that is exactly the same. These are the same. All right, it's like using a variable X instead of a variable Y. I'm using A minus instead of B. All right, so it's just a different way to do it. It is the way that I like to do it, and I will always do it that way. Again, liquid water not included. Of course, the other generic, if you like the way the book does it and uses B, H2O, HB plus, that is exactly the same thing. All right, so what we do know is that OH minus is a strong base. So OH minus is a strong base. So obviously it's going to be stronger than the base on the other side. So you have a weak base. So this is a weaker base. All right, remember the strongers and the weakers are always on the same side. And so if you're looking at water, that is going to be the weaker acid. And you look at your HA or your HB plus, that is going to be the stronger acid. So now you see that when you have water with a base, it acts as an acid. In the previous one, we had the acid HA and added water. The water acted as a base. So if you stick an acid with water, the water acts as a base. If you stick a base with water, the water acts as an acid. All right, so here, just like we had for our Ka reaction, all right, so the Ka, and now I'm going to tell you that this K value here, so this is now, I'll label it for you there, is Kb. All right, but again, it is Kc. They're both Kc. All right, but they have special letters because the A indicates that's the equilibrium constant for a weak acid. The B indicates that's the equilibrium constant for a weak base. All right, so both strongers are on the right. All acid-base reactions always favor the weaker acid, weaker base, and so we are going to favor our reactants. And so, of course, this is your concentration of your products over the concentration of reactants. And since it favors the reactants, that means we're going to have a lot of reactants and very few products. Every Kb value, just like every Ka value, is going to be a small number. They will all be able to do successive approximations. Every Kb, when we get to our list of Kbs, will all have negative exponents. They are all less than 1. All right, so here it is. Here's your Kb values, and you look at your exponents. All of these are negative exponents. They are all small values. They are all less than 1 because you form a strong base, OH minus. So that means the equilibrium favors the other side, the reactants. Every equilibrium constant for that is less than 1. All right. So here's the same reaction again, where you have your KB reaction. So the NH3 is your weak base. You add water. Now the difference between your Ka and your Kb is you must put water in your Kb because that's where the OH comes from. And so the base accepts the H from water and that leaves the OH minus. When you have your acid, H plus, H3O plus are the same. It is not required that you have water in your reaction. If you have water, great, then you have H3O plus. If you don't have water, fine, then you have H plus. They are the same. All right, and so here is the correct answer for figuring out if you can drop your successive approximations and just use the first one and go with it. If your initial concentration, acid or base, divided by your Ka if it's an acid, Kb if it's a base, is greater than 1,000, then you can neglect your X and you do not have to check it by successive approximations. All right, so that is where your 5% error comes in. If you have your concentration initial divided by your K of that reaction, if that is greater than 1,000, then you do not have to plug your X value back in and get another. You can, but you don't have to. All right, so morphine. All right, it is a naturally occurring base. All right, so you can write this whole thing out with your reaction. I am not going to. I am going to call that A minus, and this is where you might prefer the way that they do it. All right, because they're going to call it B. B is a better symbol for this because it doesn't have a charge. All right, I'm not going to change my method. I always call a weak base A minus. So I'm calling this B or A minus. I'm going to call it A minus. If you like to call it B because it doesn't have a charge, that is fine with me. All of my weak bases I call A minus. And then I have to do a base must include water because that's where the OH comes from. And so I have my HA and I have my OH minus, and that's in equilibrium. All right, the KB is given. KB is 1.6 times 10 to the minus 6. All right, and then my initial concentration of my weak base is 0.0075. All right, so what I want to know is, can I just neglect my X or do I have to check it? So what I'm going to do is now calculate the CB over the KB. And so I'm going to take my 0.0075 and I'm going to divide by 1.6 times 10 to the minus 6. And this is going to be a close call on this one, 0.0075 divided by 1.6 times 10 to the minus 6. And that gives you 4,700. All right, so it is greater than 1,000. All right, and so this one is, in the 1,000, so it's not going to be great, but it's going to be within a 5% error. And so that means we don't have to check our X value. All right, so we had zeros on the right, so it has to go to form some. So minus X, plus X, and plus X. And so at equilibrium, we have 0.0075 minus X, we have X, and we have X. And so we have X squared over 0.0075 minus X is equal to our KB of 1.6 times 10 to the minus 6. And since our ratio of our initial concentration over KB was greater than 1,000, we can neglect the X and we don't have to check it. And we will find here that we probably should have checked it. All right, it was really close it was just 4,000, just barely greater than 1,000. All right, so we have 0.0075 times 1.6 times 10 to the minus 6, and then the square root of that. All right, and we get 1.1 times 10 to the minus 4. So your X value 1.1 times 10 to the minus 4. All right, so if we want our concentrations, all right, our concentrations are right here. We got to plug X back in. So the HA is 1.1 times 10 to the minus 4 molar. The OH minus is 1.1 times 10 to the minus 4 molar. And our A minus, our weak base, is 0.0075 minus 1.1 times 10 to the minus 4. And when you plug that in, you see that it will change. So the successive approximations basically said X is so small it's not going to change our initial concentration. Well, it did. It is 0.0074 molar. All right, so that indicates that if you did X2, it might change. That's as high as it could be, and it depends on where it's rounding at. And that was a probably not going to change, but it might have changed to a 1.0 times 10 to the minus 4. But again, that's less than a 5% error, and we're going to take that as the answer. All right, so now the question was calculate the pH. And this is where you will do all this work and then get to the final step and screw up the final step. Do not do that. You must think on every single question in this chapter. This is the hardest chapter in the book because you have to think about every single part of every single problem. All right, so here you have X, and if you just write X, that's not going to do you much good. You must say that here that my X value, that is equal to my OH minus concentration. When you're doing your Ka, well, that's equal to your H plus concentration. Kb, it's equal to your OH minus concentration. And so you're not going to go right to pH. The way I do it is I go to pOH. And that is my negative log of the OH minus. So if I take the negative log of 1.1 times 10 to the negative 4, I get 3.96. So a lot of people will say that's the pH and circle it. And, well, the first thing that you see is you have a base in water. The pH has to be greater than 7. So 3.96 is definitely not a pH. A pOH, yes. All right, and so then you know that your pH plus your pOH will equal 14. And so that is an equation that you will use a lot. Your pH plus your pOH is equal to 14. And so we simply have our 14 minus the 3.96 to get the pH of 10.04. All right, so now you have a base in water and your pH is 10.04. That is a possible correct answer. Yes, it is the correct answer. All right, the other way that you can do it, because a lot of times it will ask for the concentration of H+. All right, so we're also going to have Kw, which is equal to your concentration of your H+, again, or H3O+, and your concentration of OH minus multiplied together will always be 1 times 10 to the minus 14. All right, and so once you have your 1.1 times 10 to the minus 4, you take 1 times 10 to the minus 14 and divide by 1.1 times 10 to the minus 4. And that will give you your H plus of 9.1 times 10 to the minus 11. All right, so your H plus concentration is 9.1 times 10 to the minus 11. Another way to get that is if you have your pH, you can plug that into the pH equation, and you get your H plus concentration is equal to 10 to the negative 10.04, and 10 to the negative 10.04, if you plug that in on your calculator, 10 to the negative 10.04, that gives you 9.1 times 10 to the minus 11. So whether you want to go, it doesn't matter which way you do it. I always go pOH to pH. And then if they want the concentration of H+, I take 10 to the negative pH. You could also use the Kw to get your concentration of your H plus, and then take the negative log of that to get your pH. Either way, your pH is 10.04. And both ways are basically the same exact thing. All right, so they work it out for you. You got your initial, your change, your equilibrium, and then you plug it into your Kb. They do not show the calculation of your Cb over Kb. That should be shown here, and that is then greater than 1,000. Therefore, I'm going to neglect this minus x and get my answer of 1.1 times 10 to the minus 4. All right, and so once you have your 1.1 times 10 to the minus 4 for your OH, you can plug it into your Kw, calculate your concentration of H3O plus, which is what we got, 9.1 times 10 to the minus 11, negative log of 9.1 times 10 to the minus 11. Again, your pH is 10.04 for that weak base. All right, salt solution. So this one is interesting. It's going to give you a salt. So the most common salt, NaCl. And they're going to say, all right, I got water, pH is 7. I throw in some salt. What happened to the solution? Did it become acidic? Did it become basic? Or did it not change and it is still neutral? All right, depends on what salt. The salt we add here is sodium chloride. All right, so we break it into the ion, Na plus, and the anion, Cl minus. Well, Na plus, as we know from chapter 4, it's a spectator ion. It has nothing to do with anything except for balancing a charge. All right, and so this has zero effect on the pH. It is always a spectator ion, doesn't matter if you put it there or not. All right, and you can get that by seeing that NaOH is a strong acid. So that's a strong acid. And so if you have your Na plus from your NaOH, that has, again, it's always soluble. If you have NaOH, the first thing I always tell everybody to do is to get rid of the Na. All you have is OH minus. Na plus has no effect on anything. You get rid of it. What you're working with here is OH minus. Now the anion part, that's when you have to look at the conjugate acid. And so the conjugate acid for Cl minus is HCl. That is, of course, one of your memorized 6 strong acids. And what do we know about acid strength and conjugates? Well, we know that the stronger the acid, the weaker the conjugate base. All right, and so this is a strong acid, and so this is very weak. It is so weak, it doesn't change the pH at all. So no change in pH. The only anions that do not change the pH are the ones that are conjugates of a strong acid. So there are 6 of them. All right, so since this is the conjugate of a strong acid, then you have a very weak base, so weak that it does not change the pH at all for water. All right, and so if you have NaCl, then you're still neutral. So if you're adding salt to water, you are not changing the pH of that water. The pH is going to be the same before and after you put in the NaCl. Has no effect on your pH. All right, well, what about NaF? All right, we already know about Na. I guess I got to pick a different ion. All right, so say let's pick a different one, Kf. Again, what we have for that rule, potassium salts, always soluble. Potassium has nothing to do with the problem at all. All right, and so again, you could look at that as knowing KOH is a strong base because the K has nothing to do with it, and it's just OH minus. All right, so now we look at the F minus. So the F minus, well, the conjugate acid is HF. All right, well, HF is not one of the 6 strong acids. This is a weak acid. All right, and so the conjugate of a weak acid is a weak base. All right, but it is a base, so it is a weak base, not like Cl minus, which is an extremely weak base, so weak that it was not any effect on the pH. All right, but this is a weak base that will increase the pH. And so when you stick KF or NaF, would be the same question, in water, it's going to become basic. All right, because the F minus is basic. The K has no effect. The Na, if it was NaF, it has no effect. The F minus does have an effect because it's a conjugate of a weak acid, and so that would be a weak base in water and would give you a pH greater than 7. All right? Yeah. No, the reaction is the KB reaction here, where you would have your F minus with water, because that's all you have is F minus with water. And we want to know what happens to that pH. All right, and so that's the KB reaction where it's going to form your OH minus and it's going to form your HF. Correct, yeah, right, because it's a proton acceptor. It's taking the proton from the water. The water is now acting as an acid, and then that product is OH minus. So, right. So you're getting an increased concentration of OH minus in this reaction. And so it's going to have a pH greater than 7. Whereas if you did the same thing with your HCl, Cl minus plus H2O, that's going to give you the same, it looks like. It's going to give you your OH minus, but it's also going to give you HCl. Well, since we know HCl is 100% ionized, and that's H plus, H plus and OH minus is going to give you water. The Cl minuses actually will cancel. If you did the net ionic here, the HCl becomes H plus and Cl minus. Well, the Cl minus cancels out in the overall reaction, and adding Cl minus is the same thing as just having water. Whereas HF does not 100% ionize, you cannot break that into H plus and F minus and cancel it out. Oh, there's a third choice too that's interesting. So let's say we have, which one do I want to pick? Oh, let's pick this one first. All right, so here's an interesting one. The NH4 ones are always interesting. So let's pick ammonium chloride. All right, we just did chlorine. We know that that does not have any effect on the pH. It is the conjugate of a strong acid. So now we will look at the NH4. All right, so the NH4, so it has a reaction with water. All right, and so that reaction with water is, well, NH4 has an extra H. It is going to donate the H to the water and give you H3O plus, and it's going to give you NH3. All right, and so your NH4 plus is going to make your water acidic. And so your compound ammonium chloride, if you throw that in water, again, the Cl is just going to cancel out and it's just water. That has zero effect on the pH. But your NH4 plus will donate a proton to the water to give you H3O plus, which means that this is going to be acidic. All right, and so your NaCl, it stays neutral. Your KF or NaF, that is going to be basic. Your ammonium chloride, that in water is going to be acidic. All right, so you'll be given salts and you'll have to determine if you throw that salt in water, what's going to happen to the pH. All right, so here they're saying the Na plus, so this is the NaCl. So your Na plus has no effect. It has no reaction with the H2O. The Cl minus has, again, no reaction with the H2O. If you write it out, you get the Cl minuses canceling, and it's just water. And so it is zero effect there. If you wanted to write the reaction here, that would be, you would get NaOH. All right, so your Na would go with the OH, and then you would get your H plus. All right, And you know, what do you know about that? All sodiums are soluble, so you would break this up, Na plus, OH minus. And again, just like the Cl, for your net ionic, the sodiums always cancel out. Sodium's always a spectator ion. It never shows up in the overall reaction, so it doesn't do anything. And so Na plus does not have any effect. You do the same thing down here. We already did it on the previous one. You get your HCl and you get your OH minus. And now for the 6 strong acids, that's when your Cl minus, your anion would have no effect, because only the strong acids break out 100% into H plus and Cl minus. And then for your net ionic, they cancel out, and it's basically all you have left is water. All right, and so for your ions, your anions, if they are forming a strong acid, which means they're the conjugate of a strong acid, then they will have zero effect on your pH. If your cation reacts with water to make a strong base, which means it 100% ionizes, it's going to cancel out, and again, all you're left with is water. It would have no effect on your pH. All right. So here's the NH4. NH4 reacts with water to give NH3 and H3O+. All right, so anytime you are forming H3O+, your pH is going down. It's going to become acidic. All right, so let's do this one. Let's try. Let's combine a couple. How about NH4F? So this is one where if the choice is acidic, basic, neutral, or not enough information to figure it out, here is the one where it is not enough information to figure it out, because your NH4 says it's an acid. That goes to H3O plus or H plus and NH3. The F minus says it is a base. All right, so we have our F minus plus water goes to HF and OH minus. All right, so the NH4 says it's an acid, F says it's a base. Which one is it? All right, so now you have to look up the Ka and the Kb. So you find the Ka for your NH4, you find the Kb for your F minus. All right, and so then if your Ka is larger than your Kb, then it will be acidic. If your Kb is greater than your Ka, then it's going to be basic. All right, so the other ones, one was neutral and then the other one was a base. Okay, well, it's going to be basic. All right, so if one has no effect and the other one is basic, it's going to be basic. If one is acidic and the other one has no effect, it's going to be acidic. But if one is acidic and one is basic, the way that you figure it out is you have to find the Ka value for the acid. You've got to find the Kb value for the base. If your Ka value is larger than Kb, it would be acidic. If your Kb value is larger than your Ka, then it would be basic. So if you had a chart, then you could figure it out. If they don't give you a chart, then the answer to that is not enough information to get that answer. All right, so K, remember, so K plus, it plus water, that would give KOH and H plus, but remember that KOH is a strong base, and so that breaks up completely into K plus and OH minus. K has zero effect on water. It's just like water because the net ionic is just water. You didn't do a thing by adding a K plus. Same thing with the Cl minus. So the Cl minus, it reacts with water. It doesn't, but if it did, it would give HCl and OH minus. But we know that's a strong acid, so it breaks up completely into H plus and Cl minus. And the Cl minuses cancel. It is just water. So just like your NaCl, your KCl is a neutral. You throw KCl in water and it doesn't change the pH at all. All right, we already did the NaF, the Na. Again, it's the same as the potassium. You would get NaOH. It's a strong base. All sodiums are soluble. It breaks up. It cancels. You're left with nothing. But your F minus does do a base reaction. The F minus plus H2O, that gives you your OH minus and your HF. HF is a weak acid. It doesn't break up completely into H plus and F minus, so the F minus would cancel. It stays just as written, which means you are going to get some OH minus. This is basic. Zinc nitrate is an interesting one. So you have zinc plus 2, and that will react with water. Now it'll react with 2 waters, and you would get zinc OH sub 2 plus 2H plus. All right, and zinc hydroxide is not one of the 6 memorized strong bases. If it was a strong base, it would ionize completely. The zinc would cancel out. Now your NO3 minus, if you do that reaction, plus H2O, you get HNO3 and OH minus. Now you need to know that that's one of your 6 strong acids, which completely breaks apart, 100% ionized, H plus, NO3 minus, NO3 minus in the net ionic is gone. It's just water. You didn't do anything by adding NO3 minus because that's the conjugate of a strong acid. And so the effect is the zinc is forming H plus. It is acidic. All right, and then D, we have our NH4, and we know that the NH4 is going to give us our H plus and our NH3. All right, so that says it's going to be acid. The Cn minus is going to react with H2O to give HCN and OH minus. And that says it's going to be base. So this one says acidic. This one says basic. And so we need more information. We have to have the Ka for our NH4 plus. We have to have the Kb for the Cn minus in order to get the answer to this problem. So we look them up. Ka 5.6 2.0. All right, so we look up our Kb value for the Cn minus in the chart. It's 2.0 times 10 to the minus 5. We look up the Ka for the NH4 plus. The Ka is 5.6 times 10 to the minus 10. All right, minus 10 is much, much, much smaller than minus 5. So here, your Kb is much larger than your Ka. And so again, you have to have the 2 constants. If you don't, you cannot answer that question. Now that we have the 2 constants, we see that Kb is larger than Ka. Now we have our answer. It's basic. When your Kb is larger than your Ka, then you're going to have a basic solution. All right, so they go through all of those. Again, yes, so the last one here, you have to get the K values and compare them. All right, so here's another reason why I use the generic A minus for the base. So I'm going to write my Ka reaction, and that is HA goes to H plus and A minus. So that's my Ka reaction. My A minus plus H2O gives OH minus and HA. That's the Kb reaction. So that's the only 2 reactions that you will need. Ka and Kb. It doesn't matter what the weak acid is. Doesn't matter what the weak base is. There's the reaction for Ka. There's the reaction for Kb. All right, I'm going to add those up. All right, so I'm going to subtract from both sides an HA. I'm going to subtract from both sides an A minus. And when I add my Ka reaction with my Kb reaction, I get H2O, liquid, is in equilibrium with H plus and OH minus. All right, and from the last test, what do we do when we add reactions? What do we do with our K values? Multiply. This Kc for water is not called Kc anymore. It's called Kw, of course, means water. All right, and that is equal to the Ka times the Kb. When you add reactions, you multiply the K values. All right, now Kw does not equal any Ka and any Kb. You can't just pick, well, if you add the other two Kas, Kb. It has to be from a conjugate acid-base system. It has to be conjugates. All right, and so if you have HCN and you have Cn minus, it's going to work out. If you have HCN and you have F minus, they don't cancel. All right, and so if you didn't have conjugates, then the HAs wouldn't be the same and wouldn't cancel. The A minuses wouldn't be the same and wouldn't cancel. So the equation where Kw is equal to Ka times Kb, that acid and base has to be conjugates, or they would not cancel out to give just water going to H plus and OH minus. And Kw is a constant, and then of course H plus is a strong acid, OH minus is a strong base. The other side, water, is definitely weaker, a lot weaker. It favors the reactants, which means it has very few products. And so the actual number for Kw is a constant at 25 degrees Celsius, 1 times 10 to the minus 14. So it is a constant, and of course that is equal to, if you write the expression for your Kc, since this is water, we rename it Kw, it is the concentration of H plus times the concentration of OH minus. So for every single one of these problems, water is in there. Every single one of these problems, you have a concentration of H plus and you have a concentration of OH minus. If it says give the concentration of everything and it's in an acid, you don't think that I have to give my OH minus, but it's there. If it says give the concentrations of everything, even when you're in an acidic solution, you still have a concentration of OH minus, because the product of your H plus and your OH minus is always 1 times 10 to the minus 14. All right, so we calculated we got our Kb for Cn minus, we got Ka for our NH4 plus. So I said we looked them up in a table. Well, that was not the truth, because if you go to table 16.1, 16.1 has the Ka values. 16.2 has the Kb values. So you go to the Ka value for NH4 plus. There is no Ka value for NH4 plus in table 16.1. But if you go to 16.2, what we find is the Kb for its conjugate base. So we have the NH3 Kb from table 16.2. Same with your Cn minus. If you go to the Kb table for Cn minus, it is not there. There is no Kb listed for Cn minus. If we go to the Ka table, we see its conjugate acid, HCN, is listed in table 16.1. All right, and so we actually have to calculate the Kb for Cn minus. All right, again, they have to be conjugates. They have to be conjugates. They have to differ by 1 H. The only time that your Kw is equal to the Ka times the Kb is when you have a conjugate acid-base system. All right, and so we find our Ka for HCN. All right, so on table 16.1, the Ka, we look it up. It is 4.9 times 10 to the minus 10. All right, and so again, we have the Kw is equal to the Ka times the Kb. we want to solve this for KB. So divide both sides by KA. And so the KB is equal to the KW divided by your KA. All right. So then you plug in your KW, which is a constant, 1.0 times 10 to the minus 14. Plug in your KA that you got off of table 16.1, 4.9 times 10 to the minus 10, and you get 2.0 times 10 to the minus 5, which is what we used for our KB to decide that our NH4CN was basic. All right, so we do the same thing for the NH3. All right, and so here is the KB for ammonia, NH3. So we want to find the Ka. So to find our Ka, we simply take the Kw and divide by the Kb. So when you're solving for Ka, divide both sides by Kb. And then you plug it in. You got your 1.0 times 10 to the minus 14 divided by the Kb that you found in table 16.2, 1.8 times 10 to the minus 5. And you get that the Ka for NH3, NH4 plus is 5.6 times 10 to the minus 10. And you push the buttons. All right, so you just have your Kw divided by your Kb. Again, your Kb you looked up in the table. That's from table 16.2. So if you cannot find the Ka, then you have to go to the Kb and find the conjugate acid of that by using the Ka times the Kb is equal to Kw. All right, what is the pH of 0.1 molar? All right, so this is sodium, and this is my weak conjugate base, which I always call NaA. And here is my acid, and that is what I call HA. All right, they don't actually give the formula for it this time. All right, so what I read here is I have something that has sodium with it. All right, and so I know that my sodium never has an effect on anything. And so I get rid of my Na, and I know that I have 0.1 molar A minus. The Ka for this acid is 1.4 times 10 to the minus 5. And I want to find the pH. All right, so what I know is I have a weak base, all right, in water. So I do know that my pH is going to be greater than 7. All right, that is a good thing to note, so that your pH is going to be greater than 7, so that when you get your answer, if your pH is less than 7, hopefully you notice that there is something wrong. And the chances of that being wrong are good, because a lot of people will take and get the POH instead of the pH or whatever. So you have to think about all of these variables and what they are the concentration of. All right, and so again, you have two reactions to know. This one is your A minus reaction, so this is the KB. All right, so this is HA and OH minus. So there is no, oh, you do this, you plug and chug. No, this chapter is very hard, because you have to think about every problem and every part of every problem. So I will point out all the mistakes that I have seen. So, all right, so here is your reaction. Some people can write that, some people cannot. All right, and so, but even when they get here, they're like, okay, here's the K value, and they'll say, the K is equal to 1.4 times 10 to the minus 5, and they do everything perfect, and they get the wrong answer, because that is not the K value for this reaction. So you have to be very careful when you are looking for your K value. That is the Ka for the acid. All right, I don't want the Ka for the acid, because I have the base. I have to have the Kb for the base. So to find my Kb, I have to take my Kw and divide by my Ka. All right, again, you have to, every single part of this problem takes thought. All right, and so you take that and divide, and you get 7.1 times 10 to the negative 10. All right, so that's your KB. So the first mistake, a most common mistake in this one, is you use the KA, and no, we have a base, you have to find the KB. They don't give you the KB because there is no chart for that KB. The only way to get it is to get the KA and use the KA times the KB as the KW. All right, so now we're ready to do our change in our equilibrium. So the A minus concentration is 0.1. Water doesn't matter. We didn't add any of these. All right. So now we have to find out if we have to check our X. So we're going to take our concentration of our base initial divided by our equilibrium constant for our base and make sure that that is greater than 1,000. In this case, when you're dividing by 10 to the minus 10, I'm not even going to bother to put that in. That is, bring it up to the numerator 10 to the 10th. You're talking billions. It's like way larger than 1,000. So we can get the number. All right, so 0.1 divided by 7.1 times 10 to the minus 10. So 0.1 divided by 7.1 times 10 to the minus 10 is a giant number. And that is 1.4 times 10 to the something. My calculator, I don't feel like counting it. 1.4 times 10 to the, that's going to be 10, that's going to be 9, that's going to be 8. All right, 8. All right, so you're talking 140 million. It is a lot greater than 1,000, and so you definitely do not have to check your X value on this one. All right, but it is going to the right because we cannot have zeros. They can be small, but they cannot be zero at equilibrium. And so again, you have x squared over 0.10 minus x, and that is equal to 7.1 times 10 to the minus 10. All right, so neglect your x. Multiply both sides by 0.1, and then take the square root, and you get 8.4 times 10 to the minus 6. All right, so they want the pH, so you take the negative log of that, and you get 5.07. Here's where the other wrong answer comes in. All right, so people will say, there is your pH. Well, wrong. That is not the pH. All right, because you have to know what X is. So anytime you write down what X is, all right, you got your value for X. All right, that's your OH minus concentration. And so when you take the negative log of that number, you're getting the POH. And to get the pH, you got to subtract that from 14. And that gives you the 8.93. So it is nice at the beginning if you say, okay, I know my answer to this is going to be greater than 7, so that when you get a 5.07, you know that that is definitely not the pH, because that is not greater than 7. And then when you look, you got your X. Your X is not the H plus concentration. It is the OH minus concentration. All right, so you could go to POH, or you could go to know that your KW is your concentration of OH minus, concentration of your H plus. And so to calculate your H plus concentration, you take 1 times 10 to the minus 14 and divide by the 8.4 times 10 to the minus 6. And that gives you a 1.2 times 10 to the minus 7. No, that would be minus 9. Right, minus 9. All right, and then when you take, that is your H plus concentration. And then you take the negative log of that to get your pH, and it is 8.93. So it doesn't matter if you use the kW to find your concentration of H plus and then find the pH, or if you go to pOH and know that your pH plus your pOH is 14. Either one will give you the same pH answer of 8.93. All right, so you got to keep all of these things in mind. X is not always H plus. X is not always OH minus. H is not always H plus or OH minus. All right, you have to know what X is in every one of these problems that you're doing. You got to be very careful with the equilibrium constant K. K is given in this problem, but it's not the right K. That is the Ka. We don't want the Ka. We want the Kb. All right, so you have to watch and look at every single thing, and that's why there's so many errors that you can make. Even knowing how to do it, you do all the math right, but if you're using the wrong numbers and doing the right math, you're going to get the wrong answer. Or you have the right numbers and you can't do the math. There's all kinds of ways to make mistakes on these. These are very difficult problems. All right, common ion effect. So now we're going to have something on both sides of the equilibrium. All right, so we're going to have something that's at equilibrium. Again, you add a product, it's going to shift to the left. If you add a reactant, it's going to shift to the right. All right, so the common ion effect is going to have the effect on your equilibrium. Usually we're adding a product and then it's going to shift to the left, but it can't really shift to the left because there's always a zero over there. So basically it means less is going to come to the right. All right, so here is an example of the common ion effect. If you have acetic acid all by itself, 0.1 molar, you have a degree of ionization of 0.013, or a 1.3% ionization. All right, now the Ka is 1.7 times 10 to the minus 5. All right, so they did that calculation for you. The question is, now we need to calculate the degree of ionization for acetic acid, that's 0.1 molar, to which HCl is added, and that is a 0.010 molar HCl. Remember that that is a strong acid. All right, and so you're going to have 0.010 molar H plus, 0.010 molar Cl minus. Cl minus has no effect on the pH, but the 0.010 molar H plus has a huge effect on pH. All right, but the question here is, how is the degree of ionization affected? All right, so we have a weak acid, so you can write out the C2H3O2. I always write HA. All right, and so I have HA, I have my initial, my change, and my equilibrium. All right, and I'm going to go to H plus and a minus. Now initial, we have 0.1 molar. Now we have added HCl. HCl is a strong acid, completely ionizes into H plus and Cl minus. So now we have an initial concentration of H plus. It is 0.01. A minus, we did not add any A minus. All right, so again, at equilibrium, you can't have a zero. So it has to go to the right to form some A minus. And so minus X plus X plus X. At equilibrium, 0.10 minus X, 0.010 plus X, and X. All right, to see if you can eliminate the plus and minus X without checking, we take our initial concentration of our acid divided by the Ka. All right, and that has to be greater than 1,000. Our initial concentration is 0.1. The Ka is 1.7 times 10 to the minus 5. And when you do that, 1 divided by 1.7 times 10 to the minus 5, you get 5,882, so 5,900. All right, so it is greater than 1,000. It is 5,900. That's greater than 1,000. So that means that we can eliminate any plus or minus x. We don't have to check it. All right. So this is the Ka reaction. Always have to check that, yes, that's the Ka reaction. That is the given Ka. We are using that constant, 1.7 times 10 to the minus 5. And that is equal to your products, 0.010 plus x, but we just did the calculation. We can ignore the plus x, times x, divided by 0.1 minus x. We just did the calculation. We can ignore any plus or minus x. The x value is so small, it is not going to change it. And so we get an x value of 1.7 times 10 to the minus 4. All right, so that is x. Now to get your degree of ionization, remember, you take your x divided by your initial concentration. If you wanted percent, you would multiply by 100. This just wants the degree. So x is 1.7 times 10 to the minus 4 divided by the initial concentration, 0.1. And that gives you, in decimal form, 0.0017. So your degree of ionization is 0.0017. All right, versus what it was before, a 0.013. And so you see that your ionization, the degree of ionization has gone down a lot from 0.013 to 0.0017. All right, and so that means that less is coming to the right. The amount of HA that is ionizing, less is coming to the right. We added a product, which would increase that, it would shift the equilibrium to the left. Now, it's got to go to the right because you have a 0. But that means that less amount is going to go to the right, and you have a lower degree of ionization. All right, so while we have all of our numbers, let's calculate the pH. And a lot of people, most people, they will say, all right, there's my HA reaction, so I know that here's my x is my H plus, and I take the negative log of that. I got a 3 point something, and I'm done, off to the next one. And again, you have the wrong answer. To find the pH of this, the pH is not the negative log of x. It is the negative log of your H plus concentration. You must have the H plus concentration. And so the H plus concentration is not x. It is 0.010 plus x. So my H plus concentration is equal to 0.010 plus 1.7 times 10 to the minus 4. And if you use sig figs and you have 2 decimals minus 4 decimals, you see that the concentration does not change at all. When you add that extremely small amount, you get the exact same number. And so the pH is not the negative log of 1.7 times 10 to the minus 4. It is the negative log of 0.010. The pH here is 2.00. All right, so your H plus concentration did not change. That is the same pH as you would get if you calculated the pH of 0.01 molar HCl. So, again, the X can be H plus, the X can be OH minus, and the X could be neither one of those. What question is that? That's another question. All right, so we're going to do this one next time, where we have, instead of adding the H plus to our acid, we're going to add the A minus. So we'll have an HA and an A minus. We're going to do that calculation. That's going to be a buffer, and that's going to lead us into buffers. So on Monday, we will be going through buffers. I'm going to put a video of how to do experiment 11 on Moodle. Experiment 11 is due tomorrow, yes.